Okay, hello, learners of physics. We have looked at thermometers, and now we're going to look at what we write on thermometers, right? The scales, right, Miss Ellie?
Yes, temperature scales, the
Not the
numbers that
fishing,
you write there, what do they mean?
not the fishing scales,
Nope.
fish scales. Okay, so whenever we measure temperature, right, we will measure the changes of a thermometric property with respect to the heat added or removed. So we have been through a list of thermometric property, for example, volume, pressure, resistance, EMF, infrared, wavelengths, etc., etc. Okay, and whenever we measure temperature, we are assuming two things. So in case they ask you in paper 4, you should know what the assumptions are. Number one, there is already thermal equilibrium between the thermometric substance and the environment that you are measuring. So say you are measuring the temperature of water using a mercury thermometer. So there's equilibrium between the thermometer, the mercury inside the thermometer, and the water. All equilibrium there. Beautiful. Okay. The second one is we would assume that the variation of the thermometric property and the temperature is linear. What happens if it's not linear? Then we need to do some form of a calibration, or we draw a curve, we change the scales. All right. So this one
Miss,
is we
I have a
can see.
question.
Yes, yes, yes.
You said linear, volume, pressure, resistance, all those we looked at, were those linear? Do you remember?
They were not. So they
Keep that in
will
mind.
go through a calibration process. Later, when we do past year questions, you will see how it's being done. So later, if you decide to study more sciences, whether you go into engineering or if you decide to do any field of science, when you start an experiment, the first step is actually to calibrate all your measuring devices. Miss, have to do that? Unless your measuring device is a meter ruler.
That one no need to calibrate. Just
If
do
you are,
only.
yeah, if you are measuring the concentration of a certain solution because you want to conduct a bio or a chemistry experiment, or if you are using a slightly different thermometer, the first step of your experiment is to calibrate your instruments. Okay, so we're just going to do very, very basic ones here to show you what it's like. But you could spend the first half of your experiment just drawing the calibration curve so that you can begin taking readings.
Yes.
That was my uni life from last time.
Okay.
Okay, so here you can see that there are 3 different scales. Actually, in your syllabus, you only need to know the Kelvin scale, which is the scale that scientists prefer. And why we prefer that? Because it's more precise.
Let's start with Kelvin and Celsius first then. The weird one on the right side, we will get to that one.
Why is just for fun? Okay.
That one is for you to know.
So
Okay.
do you remember like last time we talked about fixed point, right? But what is a fixed point again? So fixed point is kind of like a reference point so that you can mark out your intervals starting from that reference point. So last time we have 2 fixed points for the Celsius scale and only 1 fixed point for the Kelvin scale. And we choose this very special point called the triple point of water. All right. But what is the triple point of water there?
Triple? Why triple? Why not double? What does triple mean though?
Okay,
When you
so
say
let's
that?
compare the fixed point between Kelvin and Celsius. So if you look at Kelvin, right, your fixed point, as mentioned in the previous video, is your boiling point. Boiling point is in inverted comma, double point. Because
Why
boiling point,
double?
100 degrees Celsius, is the temperature where gas and liquid can exist in equilibrium at the same time. Right? If you see a pot of water boiling, you see the vapor, you also see water, and you don't think it's weird. Of course, if your cup of coffee on the table begin bubbling and vaporizing, then it's time to sleep. Okay, something weird is happening. Okay, so this is a double point, or there are 2 states at the same time, and we use this as your upper limit or your upper fixed point. Okay, the second fixed point in the Celsius scale is a freezing point, which we know is 0 degrees Celsius. Okay, so this one is the freezing point of your pure water. If you study any form of chemistry, you would know that the presence of salt will change the boiling point and freezing point. So we are assuming that the water is pure.
Distilled water lah. That's what it means, huh?
Yeah. So last time in 1742, when this Anders Celsius came up with this scale, his reading might be a bit off one, because how do people make distilled water back in the days? They can only try their best. But it's not perfectly distilled. Okay. So in this case, freezing point is where a liquid and solid can exist at the same time. All right. So these are all double points. You got two states at a single temperature. So from that, what do you think triple point is, Miss Ellie?
Wow, Miss, triple point means you gas, liquid, and what's the other one? Solid at the same time, Nani. How can
Yes.
like that? Are you
So
sure?
the thing is boiling and melting and freezing all at the same time.
Oh my goodness. What this?
Yeah,
Wow,
so
okay. That's
three
kind of weird.
states existing in equilibrium. Later we will show you a video. Are we showing them a video?
Can. We can show them later.
We will show you a video of someone performing this experiment and roughly explain to you why this exists. But this part is not in your syllabus. But this kind of but you have to know that it's triple point of water. So I feel that understanding what it actually is will help you remember this fact lah. Okay, so exist simultaneously in equilibrium. Okay, so I think it's important to also understand that all these things happen in equilibrium. You could argue and say that I make a hot cup of coffee and I throw some ice inside. You see, doesn't have to be 0 degrees Celsius. Not yet equilibrium. Okay.
Equilibrium means what?
Means the amount of
This
heat flow left.
context. Oh, no heat flow.
No net heat flow left between the two different things. Okay. So I think before we show you the video, we have decided that the triple, or rather Kelvin has decided to let the triple point of water be defined by defining the term absolute zero. Miss Ellie, what is absolute zero?
Absolute zero means absolute zero. 0 degree, 0 Kelvin? I don't know. Why does he call it absolute zero? Is that maybe the point where there's no energy at all? No heat? I don't know.
Because you think about temperature, right? Temperature tells you how excited the particles are. So if you're looking at absolute zero, this means that the particles are not moving at all. And this is our 0 Kelvin. Not okay, it's 0 Kelvin.
Okay.
Okay. It's not okay. Okay, so this one is a temperature at which the atoms have no or minimum or 0 internal energy. All this definition, they can ask you lah. State what is meant by absolute zero, 2 marks.
2 marks.
State the fixed point of a Kelvin scale, 1 mark. Like that, lor.
Okay. Isn't there other names for this? I remember looking at past year, they also call it absolute scale. Sometimes they call it thermodynamic scale or something like that.
Yeah.
All those also the same
The
thing.
names are up here, lor. Which is the Kelvin scale. So, but this triple point of water is what temperature?
No. Do we need to know that, Miss?
Well, we did know that the boiling point is 100 degrees Celsius, freezing point is 0 degrees Celsius. What about the triple point?
Maybe at, let's say at atmospheric pressure lah. So where you and I are living and breathing with 1 atmospheric pressure. Is it close to 0? 0.01?
Well, this one, we can look at the state change graph, right? Or the phase diagram.
Okay, Miss Lee, the graph is here, pasted here. What is happening here?
Okay, so if you look at the red color line, right? You see the pressure axis is on the y-axis and the temperature axis is on the x-axis. So if you look at 1 atmospheric pressure, our freezing point is a very familiar 0 degrees Celsius. And and as you increase the temperature, so you can see the solid is the green region, and then at 0 degrees, solid will change to liquid. If you're at the red color line, then you have both solid and liquid at the same time. So if you increase the temperature, now we are fully into the liquid zone, liquid, all the way until the blue line, ploop, because you have increased your temperature until 100 degrees Celsius. And 100 degrees Celsius, you will begin to boil. If you increase above 100 degrees Celsius, you are now fully vapor. So because these changes happen above the triple point, because the triple point is point A. You see the intersection between the lines? So at point A, suddenly you have this weird situation where you have solid, you're at the boundary of solid, liquid, and vapor. But in order for us to have triple point for water, this pressure is very, very much more lower than atmospheric pressure. So you need to have a device to be able to pump out air until you decrease the pressure, and also to bring, it's not very much colder than ice, so it just needs to be slightly colder than regular ice. But the triple point of water is at a fairly low pressure.
Very, very low, huh? 1 atmosphere is almost here already. So this is quite low.
It should be 611.2 Pascal.
In atmospheric ATMs, well, the scale is kind of in atmospheric, so let's convert to atmospheric. Pascal convert to atmosphere is
1 over
times
1.05. 1.01 times 10 power of 5.
Oh yeah, very low lah. Okay, here you go to a lower pressure.
Yeah.
So basically what happens is, normally we only understand what is happening at 1 atmosphere because that's what we see every day in the kitchen, in the toilet, wherever lah. So we are used to seeing this double point.
This is about 0.6% of atmospheric pressure.
That's very small.
0.6, not 1.6.
Oh, 0.6. Oh,
0.6% of atmospheric pressure. So it's close to vacuum you have to remove. But the good news here is different substances will have a different triple point. So we can observe triple point for other sort of substances, as you can see in the video that we will show you now.
There's this weird thing, butyl alcohol. I don't know.
We are both quite bad in chemistry.
You can tell us what the chemical formula is.
Yeah, but here, same thing lah. So we have a vacuum setup where you need to still pump up some air, okay? And if you can see, right, when the temperature, this video is not as nice, you cannot see the temperature changing. But if this is actually performed in the lab, right, the temperature will not change one.
Ooh,
so you see that's boiling. It's boiling. It looks like boiling, right? There's bubbling. So you think that normally when it's boiling, the temperature wouldn't change. But later on, as more air is being pumped out, you are lowering the pressure. So if you remember that Y graph, when we lower the pressure, finally we will reach the triple point. Okay, so this triple point is easier to achieve compared to the triple point of water, and then some freezing will happen.
2 minutes later, triple point occurs.
Yeah.
Okay. So it's not boiling anymore already. Don't know what's happening. We'll see. What's happening? Oh, what is this? What is this?
Does it look like ice?
Magic. It's like Elsa suddenly appear in the water tube.
Oh, but then it's still bubbling.
So is it liquid or solid?
Gas?
There's gas there because it's bubbling, but
all of the above. So this is actually what is meant by triple point. You have these three things, and if you actually do this experiment, right, you will see that the thermometer reading doesn't change. So all three of them will happen at the same time. Miss Ellie, can we look at the graph again?
Can.
Yeah.
Scroll up. Can I scroll up? Here.
Okay. So if you look at this graph, right, let's say for example just now we saw liquid, we saw that it is boiling. Okay, so you are probably pretty close to the triple point. And then when we lower the temperature, so we lower the pressure, because by pumping, this whole thing will begin to slide down. So it needs a while to adjust. Okay, so I think there are a few interesting things about this kind of graph. For example, if you want to know what is sublimation, you just increase the temperature below the triple point, your solid can immediately become vapor without going through liquid, which is your dry ice. Okay, and we all know that if, let's say, for example, you have hairspray or your rucksack, you want to spray the cockroach, you shake is in liquid form, correct? Because the pressure is very high. You compress it inside a canister. But when you spray it out, the pressure will begin to decrease back to atmosphere, and then you become vapor. Go back and spray. You go and shake the hairspray or your rucksack and see. So these are very interesting observations that we actually do. It's just that you might not know that we use this phasor diagram to help us decide how much to compress a vapor into a liquid, etc., etc. All right, so just extra stuff for you to know about. But let's go back to the scale. Okay, so now we understand that we rely on state changes to decide our fixed points because we can observe them. All right, but last time, before Celsius, there's this dude called Fahrenheit. And you know, US is weird. They are keeping to the Fahrenheit scale. So in case you go to US and study, I'll just tell you what Fahrenheit is now, okay? So Fahrenheit here, the fixed points here would be, it used to be, because this is a very old scale, he used 0 Fahrenheit as the ice bath of some salted water. Of course, then if you are a good science student, immediately you'll be thinking, how salty?
Why salt?
Because it's impossible to have purely distilled water. Last time, how can you distill water? You can go through many processes of boiling and cooling and boiling and cooling, but then there will still be some residue salt inside. Okay.
Mhm.
And then 96 Fahrenheit is the armpit of a healthy person.
What? Okay.
Because he
Why?
was just doing the thermometer and then he doesn't know what's happening.
I don't know how to draw armpit, miss. Like
Yes.
that lah.
So later, because and then he drew 96 intervals in between 0 and 96 Fahrenheit. And after that, to maintain the original magnitude of 1 Fahrenheit, they changed the lower point and upper point. So you can see it follows Celsius, but the numbers will have to change. Okay. So this is why the Fahrenheit scale is always very weird. So once we decide what our upper point and lower point is, we begin to draw divisions, right?
Yes.
So if the easiest one to understand is degree Celsius, because you and I, we have all seen a degree Celsius thermometer before. So we draw 100 divisions, each division representing 1 degree Celsius between the upper and lower points of your thermometer, right? And then
Fahrenheit,
for your
why you
Fahrenheit,
divide so much? Why you
yeah,
divide 180? I don't understand.
because 32 to 212 is 180 ma.
Oh, great. Okay, Mr.
Which
Fahrenheit.
means 1 degree Celsius is not equal to 1 Fahrenheit, the magnitude of change. So Fahrenheit is a more sensitive scale.
Miss, so that means this Celsius Fahrenheit is more of measuring changes. Not so much the, I don't know how, but it's like changes because you from 0 to 100, you chop it up. So 1 degree is like amount of change thanks to your
amount of
division
change in
between your
amount of
2
heat.
points.
Amount of change in your, because you give energy to the substances, you heat it up. Okay, but Miss Kelvin only got 1 point. Can draw interval. Can. Kelvin will copy from Celsius. Kelvin will borrow from Celsius. So Kelvin will be like, hey, Celsius, your 1 degree Celsius and my 1 Kelvin same, okay? So that means if your temperature increased by 1 degree Celsius, my temperature will also increase by 1 Kelvin. The only difference here is you and I have different 0 point. Your 0 degree Celsius for Celsius is ice. 0 degree Celsius for Kelvin is absolute zero. Particles not happening. In fact, some weird things will happen here. And I think if you know the Kelvin scale, 0 Kelvin is negative 273.15 degrees Celsius.
So cold. Oh my.
Yeah, and so precise, Miss, yes, you need to know to that precision. Is this number given to you in the exam? No.
You have to memorize this one.
Sorry, bad news. Okay, so as usual, we're going to compare the advantages and disadvantages of these 3 scales. So of course, you can see the advantage of the Celsius scale can easily be calibrated. Most people understand. Like don't really need to think, people get it. Okay.
You're most used to it lah.
Yeah.
Your
the
aircon.
disadvantage here is it depends on the environment during calibration. So we all know that water boils at 100 degrees Celsius, provided your surrounding is 1 atmospheric pressure. But what if your lab is in Cameron Highlands?
Different boiling point
Yeah, then how to calibrate? Of course, if you have a pressure gauge, you can measure the pressure on pump air and stuff like that lah. But if let's say you have no way to adjust the pressure, then it's hard for you to calibrate if let's say your environment is not close to 1 atmospheric pressure. Okay. Okay, so that is the disadvantages. So the advantages of Kelvin scale, which is what scientists prefer to use, is because it reflects the internal energy of a system. 0 Kelvin means no energy. If I double the temperature, I double the energy. This one, there will be an equation that we will do later in the ideal gas chapter. But the whole idea is it's easier for scientists to understand. If I tell you that 200 Kelvin has 100 joule of energy, let's say in this sample of gas, then 400 Kelvin will have double the amount of energy. So it's like a directly proportional thing, which you know lah, ratio is our best friend.
Very good. I like.
To the energy, then we will times 2 the KE. No such thing will not happen for your degree Celsius. You need to do some other, the equation is not so pretty lah.
It's not a straight line graph lah. It's like, never mind. We'll come to that later.
Yeah.
Okay.
But the disadvantages here, as you can probably tell, how on earth are you going to find negative 270? We're going to find that triple point of water.
We can't actually reach it, right?
we can if we have a good enough pump and be close to vacuum. So we need to remove a lot of air.
To go to outer space.
Well, we just need a vacuum pump.
So powerful to get your pressure all the way down.
Yeah. So we just need to depressurize the chamber until it's about 0.6% of atmosphere. That you can find a triple point. Then you can calibrate. Okay. So all this calibration can be done on any kind of thermometer. It can be a mercury thermometer, it can be any kind of thermometer, as long as the substance can reach that temperature reliably and it wouldn't boil or explode or something will happen. Okay, so here you can see it's a pretty nice diagram to compare the relative magnitude, because I tell you all these numbers, you also you can't really feel, because we are very used to degrees Celsius.
We only know Celsius 100 boiling, 0 freezing, then our aircon is 16 or 25 only.
I like how the Angmo room temperature is 21.
Okay lah, okay. They like cold stuff.
Yep. Yeah, so here you can see that if you look at the numbers for Fahrenheit, the amount of change is, you can see Fahrenheit goes through a bigger change. For example, if from 0 to 100 degrees Celsius, Fahrenheit will have been through 180 degrees Fahrenheit change. Okay, so this change is bigger. It feels bigger, the number is bigger, but actually the amount of heat is the same. Okay, so although the Kelvin looks inconvenient now with the 2 decimal point at the back, later when we study more about gases, you will see that it's actually the more useful scale in science, especially when you do sciences. But for the lay person, degrees Celsius is easier to understand. Okay, the numbers are something that you are used to. Also, you might be asking, then what's the benefit of Fahrenheit? Scientists use Kelvin, degrees Celsius people can understand. Then the Fahrenheit, why is it still there?
Ooh, maybe since the first time, the fella you invented with armpit of a healthy person, maybe it's related to the human.
Yeah. So it's commonly used in the medical field, and probably because a lot of the medical literature is written by the States as well. So 100 Fahrenheit is high fever. And the main advantages is your readings are more sensitive. But as usual, the disadvantage will be the same as degrees Celsius. It's dependent on the environment because you're using boiling and melting. And there's very problematic conversion between Kelvin and degrees Celsius.
Degree Fahrenheit, you mean?
Yeah. But if your friend US still want to use Fahrenheit, then we should just keep in mind that there's something there. Then you slowly learn to convert later.
Okay lah, can.
Okay, so we can now look at an example. What happens when we try to convert? So our syllabus focuses on Kelvin and degrees Celsius. So how do we convert, for example, 100 degrees Celsius to Kelvin?
Okay, let's write down a general idea first. We look at all the scale already, but then also we don't remember how to convert again. So your temperature in Kelvin will be whatever your temperature is in Celsius plus a certain number, miss.
273.15.
273.15. So specific.
Yes. Do we need to take all the decimal points all the time?
I think we might have to.
Yes. So it depends on the data that you receive in the question. If the temperature given to you is 1 decimal point, then you use 273.2. If the data given to you is 24 degrees Celsius, then you use 273. So you follow the same precision of the given data. Yeah, we look at an example.
Okay, here.
So here you can find some random data, for example, boiling point of water. So if you want to convert from 100 degrees Celsius to 100 Kelvin, because 100 degrees Celsius is no decimal point, so I'll just take 100 plus 273. Right.
Miss, can you do plus 273.15 and then round off later?
I prefer to not see that because that doesn't appear as such in the mark scheme.
So you just add lor?
So you have to show a situational awareness that you are trying to follow the precision of the given data. Okay, situational awareness. The candidate is aware and understand what is precision. For example, if you look at the boiling point of bromine, this is in Kelvin. So if you want to convert to temperature, you're going to minus 273. This is 2 decimal point. So it will be 332 minus 332.40 minus 273.15. You might be thinking, if they put 332.4, then you will minus 273.2.
0.2. Wow.
So you have to be a bit sensitive to what numbers they're giving you.
Okay lah. I don't have my calculator with me, so
Aya, copy answer down there lah.
you can see lah, okay? No.
59.25. Okay. So if you look at the other examples, it's the same idea lah. So if you look at all the decimal point, it follows. So if it's 2 decimal point, then the conversion will also have 2 decimal point. That's all. All right. So I think we are now ready to look at some past years, right?
Okay, so we'll see you in the next video. Some quick, short, and sweet past year examples to wrap up the whole chapter before we go on to the next chapter about states of matter, changing thermal properties, and all that. Okay.
Bye-bye.
See you in the example video.
Bye-bye.